All right, guys, we're going to talk about electricity a little bit more here. Talk about some more rules and laws. The one we're talking about now is Kirchhoff's voltage law. We use Kirchhoff's voltage law to describe series circuits. So it helps us out with a series circuit. This is an example. Series circuits components are connected end to end so that there's only one single path for the current to flow. So if you look at this one, it can only go in this path kind of thing. There's no other direction or offshoot for it to go to. So this is a series circuit. When we're talking about series circuits, we've got a few things that we need to keep in mind. The first thing is the current flowing through every series component is equal. So if you've got different stuff like resistors or capacitors or anything like that, the current through those things are going to be equal. The total resistance, or RT, is equal to the sum of all the resistances. So RT is equal to R1 plus R2 plus R3. So our total resistance of this circuit will be equal to all of these resistors added up. And also the sum of all the voltage drops. So if you look, the voltage across each resistor will be equal to the applied voltage. So our voltage across each of these resistors will be equal to our total voltage, which is 12 volts in this case. So now that we've got a little bit of background knowledge about Kirchhoff's voltage law, we want to just do a few things to see if we can verify that law to make sure that it's something that we can use. So first we need to calculate our total resistance. So our total resistance is RT is equal to R1 plus R2 plus R3, because we have three resistors in our example. If we take a look at our example here, should be able to see them all. Write those down really quick. So R1 is equal to 220. R2 is equal to 470. And R3 is equal to 1.2 K. All right. So all we've got to do now is add those up. So our RT is equal to 220 plus 470 plus 1.2 K. Right? So our RT is equal to 1890, which is equal to 1.89 kilo ohms. Okay? So that's our total resistance. So that's our first step to verifying the Kirchhoff's voltage law. So next we need to find the current through each component. And if you remember, current is represented by an I. So first we're going to find our I total, so our current flowing through the circuit. To do that, we're going to use Ohm's law. So we've got to get our Ohm's law triangle out here. Draw that really quick. So if I'm looking for I got to cover that guy, and then so we get I is equal to VR. So now we know the equation, and we can go back up here. So our IT is going to be equal to our VT, voltage total, over our resistance total, which we just calculated. Our voltage total is 12 from our example, and we just calculated the RT, which was 1.89 kilo ohms. If you do that math, you get 6.349 milliamps. And we know that since this is a series circuit, our IT is equal to our current through resistor 1, which is equal to our current through resistor 2, and our current through resistor 3 is also equal. So since this is a series circuit, the current through each component is equal to the total current through the circuit. All right, so that's the next step. So the next step to solve, to verify Kirchhoff's voltage law, is we need to solve for the voltage across each component. So the first one, we're going to use Ohm's law again to help us with this one. So we get our triangle going here just so we can have that. V, I, and R. So we're solving for V this time, so we're going to cover that up with my thumb. So we get V is equal to I times R. So this one should be pretty straightforward. So our voltage across resistor 1 is equal to the current of resistor 1 times the resistance of resistor 1, okay? Which is equal to all of our current is 6.349 milliamps times 220 ohms is equal to 1.397 volts. Okay. So our next one is the voltage of R1 is equal to the current through R1 times, this is supposed to be the voltage of R2, the current of R2, and the resistance of 2 is then equal to that same 6.349 multiplied by the resistance value, which is 470. And then this one will be equal to 2.984 volts. And then finally, we have to do the voltage of resistor 3, which is equal to the current across resistor 3 times the resistor value of 3, which is equal to that same 6.349 milliamps. And then this time it is times 1200, which is equal to 7.619 volts. Okay. So now we've got the resistance total of our circuit, we've got the current through each component, and we have the voltage across each component now. So with those three things, we should be able to verify Kirchhoff's law, voltage law here. And to do that, we have to remember what we said Kirchhoff's voltage law was. What we said it was V total is equal to the voltage across R1 plus the voltage across R2 plus the voltage across R3. So if those two sides of this equation are equal, we have verified that our law works. So we know our V total is equal to 12 volts. Our VR1 was 1.397. Our VR2 was 2.984. And our VR3 was 7.619. And if you add those up, you do get 12, right? So 12 equals 12. So we have verified, right? Our Kirchhoff's voltage law is correct, and we can use that to help us solve problems in class now.